In this video, I will talk about real-time tangible solar irradiance analysis in UC Winroad. Oftentimes we're asked to do solar incidence analysis to understand where we can put solar panels on the buildings, or new facilities that we may install on our campus. This involves identifying locations, running analysis for each of those locations, then getting feedback, changing the locations, and rerunning the analysis. Each analysis takes about a day to run because the algorithms that we use in ArcGIS are single-threaded and quite slow. Regardless, we can still compute our entire campus, but it takes about 2 or 3 days to compute for all days of the year. Google has a similar project to what we want to do, or what we have implemented, which is called Project Sunroof, but focuses primarily on analyzing residential roofs for solar potential. We've implemented a GPU version that takes only a couple of seconds rather than days, and are in the process of validating it. The basic procedure for the algorithm starts with the buildings and the sun. By knowing the sun's location in latitude and longitude, we can compute its exact position in the sky and then use that information to provide a vector to the buildings that we're going to analyze. As the sun is in different parts of the sky, it has a different amount of atmosphere that it has to travel through, called the air mass. We can use formulas to compute how much air mass that there is based on the angle that the sun is at. Once the sun reaches the surface, which we can compute from the first derivative of the height map, we can then compute direct reflection, diffusion, absorption, and transmission, if we know the materials. But for now, we focus mostly on just computing the solar irradiance that's incident to the surface as the maximum potential solar that you could capture using solar panels. Our method involves having a main application written in C++ that uses GPU shaders, or a set of shaders that computes from a height map and additional information the summed solar irradiance. UC Winroad can be used to provide a height map in JSON format that we can send along with latitude, longitude to our socket server that brings in the input to our GPU shaders. Additionally, we can choose a date-time range, which could be an interface similar to this, using hours and days of the year to specify particular ranges, such as June 21st, or the entire month of December, or only the hours at 2 p.m. Once it's computed, the output goes to an image through a socket server and can be brought back into UC Winroad or other sources for projection onto the physical surface or virtual surface. Additionally, we provide tangible interfaces with a Connect, where we can have a table with several custom magnetic cubes that we can scan and get the building's topology. These cubes allow one to move the building's shape around to change the architectural massing, but also move the position and rotation of the building to understand other performance effects in addition to solar analysis. So again, it goes from the Connect to processing the height maps to extracting buildings to sending that back out through a socket server, which could be received by UC Winroad, and again updated through this entire process. So this is our proposal for integrating real-time tangible solar irradiance analysis that we've developed into the UC Winroad as a process for users to use a more intuitive interface for solar analysis and understanding what's going on in the built environment.